salt water on either side, both with the Chesapeake Bay and then with the Atlantic Ocean, the salt water isn't very deep beneath the water table, and the more water we withdraw from those aquifers, the closer the salt water gets to the surface. All right, and then it also increases crop productivity using irrigation. We have a lot of water in the Maryland area, but it has been shown to be a fact that if you are using irrigation on your crops, even in a wet area, you are making sure that the crops get water specifically when they need it. So you can have a much better crop productivity if you're putting water on the field specifically when they need it rather than just when it rains. Okay, so knowing that water recycling is important, what are we doing with water footprinting and sort of what is it? So it's divided into 3 parts. Your blue water is water that has been sourced from surface or groundwater resources and is either evaporated, incorporated into a product, or taken from one body of water and returned to another or returned at a different time. Irrigated agriculture, industry, and domestic water each can have a blue water footprint. Green water is precipitation that is stored in the root zone of soil and evaporated, transpired, or incorporated by plants. It is particularly relevant for agriculture, horticulture, and forestry products. And gray water, and this one takes a little bit to understand because there are many different definitions for gray water, but it's the amount of fresh water required to assimilate pollutants to meet specific water quality standards. We're not talking about gray water, black water that comes out of your household where gray water is like shower water and black water is septic water. We're talking about specifically the amount of clean water that you would need to use to dilute currently polluted water into standards that are acceptable. The gray water footprint considers point source pollution discharge to a freshwater resource directly through a pipe or indirectly through runoff or leaching from the soil, impervious surfaces, or other diffuse sources. Okay. So why our water footprinting is useful? So it was introduced in 2002 as a supplement to or sort of a hybrid of carbon footprinting and emergy. And if anybody has taken a class with Dr. Tilley, you probably know what emergy is. But for those of you that don't know, it's an expression of all the energy used in the work processes that generate a product or service in units of one type of energy, normally solar energy. So water footprinting is doing the same thing as emergy or carbon footprinting. We are looking at how much water is used to create a product. Luckily for us, we are doing agricultural water footprinting, which is fairly basic and straightforward. So it's a great introduction to water footprinting. Let's see. So we consider freshwater to be a valuable commodity. It improves your overall water quality, and it looks at direct or indirect water use with the goal of eliminating waste and maximizing efficiency. Basically, when you know how much blue, green, and gray water you are using, you can also look at opportunities to trade some of that out to see if you can substitute in some blue water for green water if it's worthwhile, or green water for blue water, or blue water for gray water. And we'll get into that a little later. Okay, so the use of recycled water for agriculture. Who does it? So Israel is probably the leading nation in the world. They have a very sophisticated water recycling process. They recycle 90% of their wastewater, and 85% of this water is used in agriculture. That's pretty huge. Spain, who is second, only reuses about 20%, but 71% of that 20% is used in agriculture. And then other countries that also do water recycling for agricultural use: Australia, China, Greece, Italy, Kuwait, Mexico, Singapore, South Africa, Tunisia, and Namibia. So there are several countries out there already that do water recycling. The United States does some on a somewhat limited basis. California has actually been doing water recycling for agriculture since the early 1900s. And Delaware has been working with some sort of water recycling since the 1970s. Other states that have joined since the turn of the century would be Colorado, Arizona, Florida, Nevada, and Texas. Most of these states, you're looking at water shortages. Florida and Delaware are using recycled water to reduce aquifer withdrawals in an attempt to slow or eliminate land subsidence or saltwater intrusion into drinking water supplies. And this would be one of the big reasons that Maryland would be looking at it as well. So our study area, the Choptank watershed. On this map, you can see that it is divided into 3 sections. You've got the lower Choptank, the middle Choptank, and the upper Choptank. And all of the light green is agricultural land. The green dots that you can see are the wastewater treatment facilities, which again will come into play later. So just bear in mind that they're sort of spread out. There's not as much in the lower Choptank, but there's also not as much land down there. Okay, so Choptank watershed land use. The Choptank is a major tributary of the Chesapeake Bay. It's located on the Delmarva Peninsula. The watershed itself is 1,756 square kilometers, and 58% of that watershed is agricultural cropland. 33% is forested, only 9% is urban. They also have a lot of rules and regs from Maryland Department of the Environment out on the Eastern Shore regarding protected agricultural land and tax benefits for people who have larger plots of land that allow it to be used for farming. So there are a lot of 10-acre farms here, there, and everywhere of people who have waterfront properties and rent out 8.5 or 9.5 acres of their 10 acres to farmers who, you know, are building up a larger collection of agricultural land, beginning with little 9 and 10 acre plots. Bottom line is we don't anticipate that this overall land use ratio is going to change much in the future. The other thing to note for the purposes of our research is that corn is 23% of the agricultural acreage. And this is important in part because it gives us one very solid crop to research. And specifically, corn is something that definitely needs irrigation to be able to meet its maximum production requirements or hopes. Okay, so we're going to start looking at how water footprinting can analyze and how changing up what water use is put into corn irrigation. So your blue water footprint, again, your water evaporates, water is incorporated into your product, in this case, corn. Water does not return to the same catchment area as it came from. For example, it is returned to another catchment area or the sea, or else your water does not return in the same period. For example, it is withdrawn in a scarce period and returned in a wet period. Basically, you can look at blue water as irrigation water from ground or surface water sources. Now, a quick crash course on your Eastern Shore aquifer system to make this make more sense. Most of the groundwater systems that Maryland uses for irrigation are the Aquifer, the Cheswold, the Federalsburg, the Frederica, and the Piney Point. And on this, it's a little hard to see them, especially if you don't know what you're looking at. But the Piney Point is the dark brown at the bottom. And all of the ones in sort of the pinks and purple are your Cheswold, Federalsburg, Frederica. And sorry, not Piney Point. The Aquifer isn't really even on here. And that's because this came out of the Delaware Geologic Survey. The reason I had to pull this from the Delaware is because if you look at the Maryland map, all of these aquifers up in the upper right that are green that say surficial aquifers, the tertiary age minor aquifers and confining units, all the way down to the Piney Point aquifer, those are the ones that we're talking about that are used as agricultural and drinking water irrigation sources. So we're talking about, as far as the aquifer systems go, a very narrow band of aquifers that the Eastern Shore has access to. Most of the rest of Eastern Maryland, Anne Arundel County, St. Charles County, are going to get their water from the upper Patapsco, the lower Patapsco, and the Patuxent. And you can see that those are much larger aquifers that have a great deal more water. So as you withdraw from the aquifers, you have the potential to compact any clay-based aquifer system, which means it cannot be renewed. You also then begin land subsidence, because as that land compacts, it goes down. So you can see that we don't have a lot of groundwater to work with, and it's really important to remember that this water is used for drinking water almost exclusively out on the Eastern Shore. Okay, so the blue water analysis is really pretty straightforward when you're talking about the blue water for irrigation, because it really does kind of come down to your groundwater withdrawals and your surface water withdrawals. So here is a quick summary of all of the water on an annual basis when they did it in 3 different years, 2000, 2010, 2015. They skipped 2005 for a groundwater study. But these are your water withdrawals in the Choptank region. So you can see that our total blue water used, our total groundwater and surface water withdrawals out on the Eastern Shore, had a pretty steady increase from 2000 to 2010. It tapered off somewhat going into 2015, but it's still increasing. And that is what we are hoping to change or affect. So putting that in our back pocket, we're going to look at green water. So green water is your precipitation on land that does not run off or recharge the groundwater, and then it's stored in the soil or temporarily stays on top of the soil or vegetation. Basically, for our purposes, we can say that green water is effective rainfall. Now, we want to talk about the difference between just rainfall and effective rainfall, in that you can have not enough water coming out of the sky to be effective, or you can have too much, which means that you get overland flow and it doesn't help with your crop growth at all. So to do our green water analysis, because this was a little more detailed, I used the CropWatt system from FAO, and there are a lot of different screens to input, beginning with your climate data, which I used the Baltimore weather station. It was the closest one that was already in the ClimeWatt system, which is the sister system to CropWatt. It made it a lot easier to enter data. There is a weather station out in Dorchester that has less comprehensive information, and that would have to be painstakingly hand entered. So I'm working on seeing if there is a difference between the Baltimore averages and the Dorchester averages right now. But for the purposes of this presentation, we're going to look at Baltimore. So you enter your weather data, you enter your rainfall data, and then you can enter what kind of crop you are doing, in this case, corn, with a planting date of not in this picture, but in my research, I did April 11th. I had to count it out. And then it gives you sort of the input of the overall crop growth in decades. That's 10-day intervals, and how deep the roots go and how much water it needs for that particular growth stage. You can then enter your soil type, and they have very broad soil types. So I did a red loamy soil, since most of the soils out on the eastern shore fall into sandy loams or loamy sands or silt loams. This one was the closest profile. Again, if you want to get really specific in an acreage by acreage analysis, or if you want to do a field by field analysis, you could do some really great work with exactly how much water each crop needs in each space, given the soil profiles that you're working with. So again, because I'm trying to do the Choptank overall, this was the closest one that I could get to that kind of covered everything. And once you plug all that in, you get your crop water requirements, and it will tell you the stages, again, in the decades, with your initial, your development, your mid, and your late stage. And then it will tell you your evapotranspiration, your effective rainfall, and thus your irrigation requirements. And from here, you should be able to do a much better job managing your crop irrigation. In water scarce regions, this is especially helpful because you can put as much water as needed without too much. And in places like Maryland, you'll be able to analyze, well, even though we have rainfall, there are specific growth stages where you need a lot more irrigation to really get maximum productivity, and you'll know going in exactly when those are and exactly how much water you need. Okay, so those results a little more clearly, a little larger here. So you can see we've got in right at the end of the development stage in May and June and July through the mid stage, there is a huge increase in the amount of irrigation required. And part of that is because June and July in Maryland are rather historically dry months. It is interesting, maybe ironic to note that Maryland's wet season is January through April. So your best rainfall is happening right up to the point that you plant these crops, and then it starts to go away for the hot, dry summer. Okay. So if you're not using CropWatt, you can find your effective rainfall using the SES method of calculating your effective rainfall by plugging in all of the numbers. So at least there is a way to do this at a much more specific level. The reason that this is important to me is because your effective rainfall and your irrigation requirements when using CropWatt are done on monthly averages. And one of the things that we have noticed in Maryland, here you have your historic daily rainfall patterns. The top one is your total rainfall across several years, specifically in growing seasons. You can see that we're getting an overall increase in the amount of rainfall that we're getting year over year. It's a pretty steady increase with some cyclical highs and lows. However, your days with effective rainfall or your days without effective rainfall, your zeros and your effective rainfall, those blue and green lines, are staying pretty consistent. So what that tells us is that even though we are getting more rain overall year over year, we're not getting it in more days with rain. We're just getting larger, heavier storms when we get them. And if you go back to the idea of effective rainfall, if your crops can only absorb, or your soil can only absorb 30 millimeters of rain on a 24-hour-a-day basis, if you get 1.2 inches or 3 inches or 5 inches, you're still only going to get that basic input every day. So even though we're getting more rain, it's not necessarily more effective rain. The other thing to note here is that because we're getting more rain, but it's not coming on more days, going back to the idea of being able to calculate your effective rainfall day over day means that you've got a better chance of really honing in on what days and times you're going to want to irrigate. Okay. So The other thing that is interesting to note with your effective rainfall are your predicted rain trends. Aminashi, who now works for UMD, did a research paper, and in here we talk about predicted rain trends. We had two of them, and one of them overall for sort of the eastern area, for the Maryland region, we're looking at a minor increase of 1.34 degrees Celsius and a 6% increased rainfall, again, bearing in mind that that increased rainfall tends to happen in clumps and not in additional days. So what happens if we have this increased temperature and this increased rainfall? Our effective rainfall ends up being a little higher, and our irrigation requirements, though, also increase a little. And I know that you didn't look at the bottom and remember what our original rainfall trends were when I showed them, but that's okay, because here in 2 slides, I'm going to put all of this together and you'll be able to see them side by side. The other predicted trend we have is the maximum end with 5.78 degrees Celsius and 36% increased rainfall. So again, we'll see an effective rainfall that increases a little bit, and irrigation, though, that also increases. I think it's pretty interesting to note that even though our overall even though our overall rainfall is increasing, our irrigation needs are also increasing. So here we have them side by side for comparison. Currently, we are getting approximately 4,124.4, and my apologies, that's millimeters or liters per day per acre. However, if we increase it just a little, we've got a small increase of the 7.1% increase in rainfall there. And if we go to the maximum predicted increases, we've got a 25.6% increase in rainfall. Likewise, with our irrigation, we've got a 1.2% increase in the irrigation needs, even for that small increase in temperature and the increase in rainfall. And we've got a 9.8% increase in the need for irrigation with our maximum temperature and rainfall increases. It doesn't seem like an overwhelming amount, but if you remember back to how narrow an aquifer band we have for pumping irrigation, it ends up being a noteworthy amount. So that is where you've got a green-blue water trade-off as we move forward with potentially higher temperatures, is that we're going to end up needing more irrigation in the future, even just keeping our agricultural levels the same. So now we get into the gray water footprint. Brace yourselves, there's a lot of math here. I tried to simplify it as much as possible for the sake of slides. So your gray water is an indicator of the degree of freshwater pollution that can be associated with any given process that you're trying to evaluate. Again, in this situation, it's agriculture. And it is the volume of freshwater that is required to assimilate a load of pollutants based on natural background concentrations and existing ambient water quality standards. You can kind of boil it down to the amount of water that is needed to make true the phrase that the solution to pollution is dilution. Now, I want to point out that even though it can be understood this way, we prefer not to use that term, since it sometimes causes confusion with people who thought that that means that we should be looking to dilute pollutants instead of reducing their emission. That's not what this does. It's just saying that given the current amount of pollution, how much water is it going to take to make that polluted water usable or non-toxic, as the case may be. Treatment of wastewater before disposal will obviously result in a reduced gray water footprint. Okay, so your gray water computation. This is a pretty straightforward formula here. It takes a little evolution to get to, but we'll start here. Where L is your pollutant load, and in this case, coming from the Maryland Department of the Environment TMDL report, there's one that is coming out next year. They release a big one every 10 years, and they have monthly and biannual updates to some of it, but they do a whole report once every 10 years. So the pollutant load that we used coming out of specifically the Choptank is 2.5 to the 6th kilograms per year. And this is specifically for, I'm sorry, this is very specifically for nitrogen. Your maximum acceptable concentration of this pollutant is 1.41 to the -5th kilograms per liter. And the natural concentration of that pollutant, if you went back to before people started any sort of industrial productivity or farming on the Eastern Shore, it is estimated to be 2.45 to the -6th kilograms per liter. So one of the things of note here is that we're trying to get down to one order of magnitude larger than where we initially were. But we've got a long way to go. So when you calculate this, you come up with a gray water footprint that is 2.03 to the 11th liters per year going out into the Chesapeake Bay. And this is again sort of the total nitrogen load. It is not point source versus non-point source. This is what is measured in the water at your monitoring stations. And then I just put the actual number in there to give you a very specific sense of exactly how much we're looking at in liters per year. Okay, so why is this relevant to our agricultural footprint? Well, let's take one more sidebar and look at gray water from your wastewater treatment plants, again, recognizing that this is the gray water of the water footprint definition. So here we have your average discharge from all of the wastewater treatment plants that are currently in operation out on the Eastern Shore. There are a couple of these that are in process, and we'll discuss this later if we have time. But there are a couple of these that are in process of researching and developing and then hopefully building treatment facilities that are improved, but most of these were built at least 30 years ago and are operating at the standards to which they were built. So you can see how many million gallons per day they discharge, and then we change that to liters so that we could keep units consistent, and that tells you about how many million grams per year we have in total nitrogen flux. So if we put those numbers back into our gray water formula, taking into account your average flow, you get 4.63 to the 9th liters per year in wastewater specific gray water. Now, what that means, and this is the part that's very exciting to me as far as recycling water, is that we've got a Choptank total of gray water that is 2 orders of magnitude larger than the wastewater treatment plant. However, flipping it over, just the wastewater treatment plants contribute 2.3% of the total gray water that is going into the Choptank. More importantly, it is 9.9% of the required irrigation water that we are currently using on corn in the Choptank right now. So if we were able to refocus that and use all of this water that we are currently discharging into the Choptank out onto the agricultural fields, we would decrease the gray water going into the Choptank River by almost 10%, almost 2.3% of its overall water. The other reason this is important, again, is your saltwater encroachment. And I have this slide in here to talk about as you pump your water, your salt water comes up and then you end up here in the upper right corner, getting to the point where you are pumping ends up pulling in your salt water, and then you can't use those wells anymore. You can't use that depth anymore. This is important because one of the projects that we will be looking at here in a moment is aquifer recharge. The 2 ways to use the gray water in irrigation for agriculture are either to find a way to convey that water directly to the farm or to do deep water injection and put it back in the aquifers for future use and to help keep that salt water from creeping up into where wells are pumping. So from that, we can look at current projects. And the first one is a Kent County reclaimed water project, which let me see if I can change this real quick. One moment. Here we go. Where did it go on mine? Okay, I'm trying to find my video, but I've got too many windows open. Here. There we go. So I'm going to play this video real quick for you. Oh no, I see that you guys have no sound. Okay, well then I guess I will abandon this and just summarize for you. Worth a shot. Screen share. Okay, so Mr. Dill is a farmer that is right up the road from the water reclamation facility in Kent County. And what they did is they looked at the water that they had just upgraded the facility, and they said this water is exceptionally clean. It seems like a shame after we spent all of this time and money making it really nice to put back into the bay, that all we're going to do is just put it back into the bay. So what Kent County did is they paid for 2 miles of forced main to the farm that Mr. Diller owns. It's 76 acres of cropland, and it gave him an irrigation system that was designed for 195,000 gallons per day with a 150-day retention time pond for storage. So that if we have wet weather, he doesn't have to irrigate, and then he is able to do an estimated 1 to 2 inches of irrigation a week when it was necessary. The result of that is that Mr. Diller has reported that irrigation with reclaimed water has approximately doubled his crop yield just to be able to irrigate using that water. So not only did he have no water before, and he was essentially completely dependent on rainfall because he didn't have any viable aquifers underneath his farm, but with being able to give water to his crops specifically when they needed it, he has doubled his yield. So that is what we're looking to do all across the Eastern Shore as these plants upgrade. And speaking of plants that are upgrading, Cambridge wastewater treatment plant, which is by far the largest wastewater treatment plant within the Choptank watershed, they have a $400,000 grant from the Bay Restoration Fund, as well as $100,000 from the Supplemental Assistance Program to design an enhanced nutrient removal system for their facilities. They treat approximately 8 million gallons of water per day. So once this is complete, the treatment plant will reduce their nitrogen discharge by as much as 62%. Which will not only significantly reduce the amount of nitrogen that goes into the bay, but will also give us the opportunity to take that water and use it on cropland. The other nice for us, is that they are looking at relocating the Cambridge water treatment plant from sort of right in the middle of Cambridge to on the outskirts when they redesign the new building. So there's that. Okay, so, oh, I just said that. All right. So the other thing that is going on right now that is exceptionally relevant to what I'm talking about is that Arundel is prepping a groundwater injection project for aquifer recharge. They did a 3-year study about septic connection alternatives, about stormwater retrofits, and about managed aquifer recharge, and discovered that the managed aquifer recharge ends up being the least expensive way to manage their nitrogen removal from their wastewater that is coming into their treatment plant. So what they are proposing and what they are working their way through right now is going through your treatment facility into your wastewater facility, and then having advanced water treatment that will then be directly put back into the aquifers underneath the wastewater treatment plant. That means that the aquifers that you are withdrawing from for your agricultural purposes will not end up affecting the overall depth of your aquifer, and you are less likely to result with compaction. All right. So what they're going to be looking at as they build their pilot facility and their test well are your trace organic contaminants, your pharmaceuticals, your personal care products, industrial byproducts, disinfection byproducts, and then heavy metals pathogens. So they'll be monitoring all of these as closely as they can in the hopes of ascertaining whether or not the water that they are treating is going to affect the overall water quality that is currently in the aquifer. And if it looks like they're doing a good job, then they're going to build 3 more wells at the facility in Arundel that they are currently using as their research. They modeled a lot of this after Hampton Roads down in Virginia. And I don't know if any of you know that facility, but Hampton Roads has a severely impacted aquifer system from a meteor that landed there millions and millions of years ago. So they have very little groundwater, and the Hampton Roads water recycling project down in Virginia is one of the most technologically advanced. I highly recommend, if this is your thing, that you schedule a tour there. So our conclusions, our summary: the aquifer system on the Eastern Shore is used as both the primary drinking water supply and the primary source of irrigation. Future rainfall trends will lead to a slight increase in the need for irrigation, and irrigation leads to significant, as much as double, crop production. So knowing all of that, using currently available treated wastewater, you can decrease the gray water flow into the Choptank by as much as 10%. The next steps, either for me or for future students looking to do similar studies, we need water delivery options and costs. We have the one research project from Arundel, but there isn't a lot detailing for private facilities or for facilities who are looking to fund this, where they can get their finances. So knowing what government grants are available, what your site-specific piping and infrastructure will look like in order to get that water out to the agricultural system, or how much wells at that particular place, because wells exponentially increase with cost as you go deeper, what the aquifer injection is going to cost at a specific location. There's also a lack of serious study in the possible pitfalls of water recycling. So researching your chemical compounds that might remain after biological contaminants are removed is a really critical step to making sure that we are not then irrigating crops with things that are potentially toxic or that would affect either people or animal health once those crops are consumed. And then we also need qualitative research on public perception of recycled water. I know from having worked a little bit on the Arundel recycling project that depending on how you phrase it and how you market it makes a big difference in how the people that are going to be using those aquifers where you're doing your injection or going to be around the crops that are being irrigated with water recycling. It makes a big difference on how people perceive that. So that is everything. I ran a little over, my apologies, but if we have any questions, I'm happy to entertain them. Ta-da.
Great. Well, thank you very much, Mary. And before we jump in and let Mary answer a few questions, I want to remind everyone that the very first chat entry is a link to an evaluation form for Mary's seminar, and we would appreciate your filling that out. You can go to that. There's a question here from Dr. Tilley asking, were you able to estimate the total water footprint for Eastern Shore corn?
That's a very good question. Yes, the water footprinting that I did for this whole project was very specifically for Eastern Shore. So you can total it up and say this is like the total water footprint, much like you would say for Emergy. So we would just take the blue, green, and gray water that was used for corn. But it doesn't quite work that way. It works better to talk about it as this is your blue water and this is your green water, and this is how much of those two would be interchangeable. This is your blue water and this is your gray water, and this is how much would potentially be interchangeable. So you can add up the numbers, but it makes more sense to use them in comparison.
Okay, let's see. Another question about, are there any statistics on the percent of the recycled water used in agriculture in the whole USA?
I am sure there are. I do not have those on hand. I would be willing to bet that Farshid has a little more information on that based on the research that I know he has done. I do know that water recycling in the US is significantly lower than it is in other parts of the world, just because we have really specific guidelines, although they do vary state by state, on what you can use recycled water on and what the quality levels have to be before you can use it. California specifically has a lot of different information on if it meets this first level, you can use it on crops that you're not eating. And if it meets a second level, you can use it on crops that are high off the ground, like trees, even if they are fruit trees or nut trees and producing food. And then it has to meet a very exacting standard that is a level 3 in order to use it on ground grown crops. So we are a long way behind the rest of the world in using recycled water for agriculture, except in California, we're getting a little closer. Most places use it for like irrigating golf courses at this point because grass is not edible at all.
Okay. There was a question about what do you think is the potential of nutrient recycling for nitrogen and phosphorus that's removed from the wastewater treatment plants for agriculture? I guess they pull a lot of nutrients out of there, and nutrients are one of the things the farmers are paying for. So how does that work?
And this is actually probably another place that could use a good bit of research, and that's the opportunity cost. The best way, as a lot of us know, to fertilize crops is with liquid fertilizers so that they sink into the ground. So if we know how much fertilizer the farmers that are using the irrigation need, you could actually set your standards to how much nitrogen and phosphorus they need, remove what they don't, and then send it out. And that would decrease your cost for cleaning the water because you're only cleaning it to the standards that the farmer needs while also giving them a more effective fertilizer. I will say that it's a gray area and it's a really slippery slope. Out in Delaware, they use chicken waste to irrigate, and A lot of the chicken farms out there do not do a good job of policing the nutrient content of the water that they are putting onto the fields that they have rented out to farmers to be able to farm. So the groundwater in that area, the surface water in that area, the discharge into the streams out there. This is another project that I worked on for my job, is really bad. So it is, I think, a bit of a slippery slope to say we can use that nutrient byproduct to help fertilize other ground. But theoretically, everything that comes out of your wastewater treatment plant as far as nitrogen and phosphorus could be reused theoretically.
So this farmer that you showed, the example where they're actually sort of pumping water for reuse directly for his irrigation purposes.
Mm-hmm.
So he's sort of on a dedicated line?
He is.
This, okay, and so of course that, the need for irrigate, rainfall is probably the most variable, one of these most variable components, certainly of climate, right? I mean, temperatures are a little more stable, but the actual rainfall that comes in at any given time is like all over the place. Mm-hmm. So are they prepared to kind of deliver on demand, or do they sort of deliver, or they need to deliver on kind of a routine schedule? How is that managed?
Sure. So I covered it, but very quickly because towards the end I was running out of time. But they actually have a retention pond that is built so that they have a very regular pumping schedule. But if they're pumping water that he doesn't need, it goes out to a retention pond and a settling pond. And then he can pump it back in when he needs it, okay. Which is the way a lot of water treatment facilities work, is they'll bring the water in and they put it in their retention ponds until they're ready to treat it and send it out into the system. He does work, and it says in the interview, I believe, I thought I saw that Dr. Azar shared the link, but I can always send it out if he didn't. He works very closely with the plant manager. So if he does need a little more, they can turn it up. And if he is getting to the point where they've had 5 days of rain in a row because of a hurricane that has come in and his ponds are close to overflowing, he can call them and they can turn it down. Most water treatment facilities are highly automated at this point. So he can go into his SCADA system and just decrease the flow, and it takes about 30 seconds.
Got it. Thank you.
Mm-hmm.
Okay, let's see. Is there one more question here? Maybe nitrogen removal at the wastewater treatment plants is often through denitrification, which can't be captured, or biosolids that are applied to the fields. Have you compared gray water to sort of biosolids contents in terms of contaminants?
I have not, but I would be very interested in doing that. Again, and that sort of, for me, goes back to seeing the misuse of that water from the chicken litter farms as compared to the responsible way that it is done currently in Kent County. So I think that is well worth researching.
All right. Well, thank you again, Mary. That was very good. We certainly appreciate that. We'll give you a hand.
Yeah.
Everyone could sort of appreciate that in these strange times. And let me remind everyone once again, there's been a couple of us added links back into the chat box. So hopefully you should be able to find your way to the evaluation form. And we thank you all for joining us. We will invite you to come back next Wednesday for our last regular seminar presentation. And until then, hope everyone has a profitable time and a good day, remainder of the day.
I'm going to, people can leave, but Dr. Felton just put up a question.
All right, missed that.
And I know this one, so I can speak to it.
Oh, well, jump right in then.
So MDE currently segregates permits based on the amount of pumping you're doing rather than the use of the water. So if you are doing a drinking water well for an entire community, like out on Kent Island at the Four Seasons community that they are building, that requires a gap analysis. and it requires making sure that your cone of influence isn't going to affect the other wells in the area. But if you've got 15 small agricultural wells that are individual, that's a totally different permitting process, and MDE doesn't actually care if you're going to use that for agriculture or for drinking water. Having said that, there are some of the aquifer systems that have higher levels of iron or even arsenic that make them non-potable, but make them something that you could still potentially use for industrial or agricultural use. And so depending on which aquifer you are drilling down to will also depend on, or will also result in a different permitting process, depending on what's around you for your gap analysis.
Great. Thank you.
Mm-hmm.
Okay, well then we will look forward to seeing everybody back next week. Thanks very much, Mary.
Thank you.